Good morning, sir. I am Jericho Canyadilla from BS Math 1B, and I'm going to report the topic entitled The Geometrical Discoveries of Tales. The Greeks made mathematics into one discipline, transforming a varied collection of empirical rules of calculation into an orderly and systematic unity. Greece and the Aegean area. In ancient Babylonian Egypt, mathematics had been cultivated chiefly as a tool either for immediate practical application or as part of the special knowledge betting a privileged class of scribes. The Greeks' habits of abstract thought distinguished them from previous thinkers. Their concern was not with, say, triangular fields of grain, but with triangles and the characteristic that must accompany triangularity. Plato's inscription over the door of his academy, "Let no man ignorant of geometry enter here," was not the admonition of an eccentric, but rather a tribute to the Greek conviction that through the spirit of inquiry and strict logic one could understand a person's place in an orderly universe. In Greece, there was no papyrus such as was available in Egypt, no clays as in Babylonia. Such books as were written must have been very few, and with the passing of time and ravages of the elements, little original materials has survived. Consequently, early Greek history is a morass of myths, legends, and dubious anecdotes preserved by writers who lived centuries later than the events under consideration. The Greeks were not always gone to the southeastern corner of Europe, their location in modern times. Although the Egyptians had kept themselves, the Greeks were great travelers. Their colonization of the coast of the offshore islands of Asia Minor from the 11th to the 9th century BC was a prologue to later large-scale movements from mainland Greece. About the middle of the 8th century BC, a network of Greek cities was founded on the coastal reaches of the Mediterranean with scattered settlements as far inland as the eastern end of the Black Sea. Down to 650 BC, the main vent for Greek expansion was Lower Italy and Sicily. The many outreaching colonies there caused the whole area to be given the name Greece in the West, although the earlier migration to Asia Minor probably the result of the Dorian conquest of large portions of Balkan Peninsula. Economic distress and political unrest in the homeland were the new incentives to spread overseas. An increase in population caused a crisis in land ownership as well as serious shortage of food. All this migration not only provided an outlet for dissatisfied elements of population at home, but also served to establish foreign markets and to its beginning in an expanded Greece. In due course, peninsular Greece became only a part of Greater Greece. By 800 BC, there was, broadly speaking, a unity of language and custom throughout of the ancient Mediterranean world. The wave of colonization that took place outside the Aegean from the 8th to the 6th century BC paved the way for an extraordinary breakthrough of reason and that attendant cultural advancement. Historians have called this phenomenon the Greek miracle. The miracle of Greece was not single but twofold. First, the unrivaled rapidity and variety and quality of its achievement. then its success in permitting and imposing its values on alien civilizations. For this, their colonies were like conduits through which Greek culture owed to the world of the barbarians and the older Egyptian and Babylonian cultures streamed to the Greeks. The Phoenician alphabet had more consonant symbols than the Greek language required, so the Greeks set out by selecting and adapting the consonant they needed. Thereafter, they assigned vowel values to the remaining symbols, adding only such new signs as they needed. For instance, infinity, which had a consonantal value in the Phoenician alphabet, became the symbol for the vowel A in the Greek alphabet. As in other matters, the Greek city-states version getting underway with as many as 10 different versions. Gradually, one of these local alphabets, the Ionian, gained the ascendancy, and after its official adoption by Athens in 403 BC, it spread rapidly through the rest of Greece. Although the acceptance of alphabetic writing did not initiate anything like popular education, the ease with it could be learned made a possible wider distribution of learning than had prevailed in the older cultures, where reading and writing were the property of priestly class. Coinage in precious metals was invented in the Greek cities of Asia Minor about 700 BC, stimulating trade and giving rise to a money economy based not only on agriculture but also on movable goods. In rendering possible the accumulation of wealth, this new money economy permitted the formation of a leisure class from which an intellectual aristocracy could emerge. Aristotle recognized how important non-practical activity in the advancement of knowledge when he wrote his Metaphysics. When all inventions had been discovered, the sciences which are not concerned with the pleasures and necessities of life were developed first in the lands where men began to have leisure. This is the reason why mathematics originated in Egypt, for there the priestly class was able to enjoy leisure. The Egyptian priests obtained positions of leadership and respect because they surpassed their fellows in knowledge. Greek education was far more broadly based and designed to produce gentleman amateurs. Geography shaped the pattern of political life. In Egypt and Babylonia, it was easy to subject a large population to a single ruler, but in Greece, where every district was separated from the next by mountains or the sea, central control by an absolute monarch was impossible. Mountainous barriers were not enough to prevent invasion, but they were enough to prevent one state from being merged with another. Patriotic loyalty was to the native city, Athens, Corinth, Thebes, or Sparta, and not to Greece as a whole. In the great emergencies, the Greek states acted collectively, seeing that they must unite or be destroyed. During the Persian invasions of the later 6th and early 5th centuries BC, they pooled their fighting forces to defeat Darius and Marathon during the 490 BC, and Xerxes they pulled their fight at Salamis 480 BC. After a rearguard action by 300 Spartans and at Thermopylae, on none of these occasions was the union successful or long-lasting, because with each victory of the city-states would promptly fall out and exhaust themselves in long local wars. The lack of political unity made the outcome inevitable. The end came when Philip II of Macedonia overpowered the mixed Greek forces. The Battle of Chaeronea in 338 BC and established himself as the head of all the Greek states except Sparta. 2 years late, Philip died 2 years later and the power passed into the hands of his son, Alexander the Great, who achieved what no leader before had done. He united Greece and carried Greek civilizations to the limits of the known world in 323 BC, when Alexander died at age 32. He ruled over conquests of more than 2 million square miles, but neither Greeks nor Greek culture vanished with the change of masters. The year that followed from the time of Alexander the Great into the 1st century BC formed a brilliant period of history known to scholars as the Hellenistic Age. The dawn of demonstrative geometry, or the tiles of Miletus. The rise of Greek mathematics coincides in time with the general owering of Greek civilizations in the 6th century BC. From the modest beginnings with the Pythagoreans, number theory and geometry developed rapidly so that early Greek mathematics reached its zenith into work of the great geometers of antiquity, Euclid, Archimedes, and Apollonius. Thereafter, the discoveries were less striking, although great names such as Ptolemy, Pappus, and Diophantus testify to memorable accomplishments from time to time. These pioneering contributors exhausted the possibilities of elementary mathematics to the extent that little significant progress was made beyond that what we call Greek mathematics until the 16th century. What is more striking still is that almost all the really productive work was done in the relatively short interval from 350 to 200 BC, and not in the old Aegean world but by Greek immigrants in Alexandria under Ptolemy. The rest, individuals with whom specific mathematical discoveries are traditionally associated, are Tales of Miletus over the series of 625 to 547 BC and Pythagoras of Samos Thales was a Phoenician descent, born in Miletus, a city of Ionia, at a time when a Greek colony flourished on the coast of Asia Minor. Ancient opinion is unanimous in regarding Thales as unusually shrewd in politics and commerce, no less than in science, and many interesting anecdotes, some serious and some fanciful, are told about his cleverness. Once, one of Thales' mules loaded with sulfur trade accidentally discovered that if it rolled over in a stream, the contents of its load would dissolve. On every trip thereafter, the beast deliberately repeated the same stunt. Thales discouraged this habit by the expedient of filling the mule's saddlebags with sponges instead of salt. This, if not true, is certainly well invented and more in character than the amusing tale Plato tells. One night, according to Plato, Thales was out walking and looking at the stars. He looked so intently at the stars that he fell into a ditch, whereupon an old woman attending him explained, "How can you tell what is going on in the sky when you can see what is lying at your feet?" This anecdote was often quoted in antiquity to illustrate the impractical nature of scholars. As we have seen, the mathematics of the Egyptians was fundamentally a tool crudely shaped to meet practical needs. Thales is generally hailed as the first to introduce using logical proof based on deductive reasoning rather than on experiment and intuition to support an argument. Thales was the first to go into Egypt and bring back this learning, geometry, into Greece. He discovered many propositions himself, and he disclosed to his successors the underlying principles of many others. In some cases, his methods being more general, in others more empirical. Modern reservations notwithstanding, if the mathematical attainments attributed to Thales by such Greek historians as Herodotus and Proclus are accepted, he must be credited with geometric propositions. An angle inscribed in a semicircle is a right angle. Second, a circle is bisected by its diameter. Third, the base angles of an isosceles triangle are equal. Fourth, if two straight lines intersect, the opposite angles are equal. Fifth, the sides of similar triangles are proportional. And lastly, two triangles are congruent if they have one side and two adjacent angles respectively equal. Because there is a continuous line from Egyptian to Greek mathematicals, all of the listed facts may well have been known to the Egyptians. For them, the statements would remain unrelated, but for the Greeks, they were the beginning of an extraordinary development in geometry. Conventional history inclines in such instances to look for some individual to whom the miracle can be ascribed. For the orderly development of theorems by rigorous proof was entirely new and was thereafter a characteristic feature of Greek mathematics. Measurements using geometry. Several stories purport to illustrate Thales' interest in Egypt. There are two versions of the story. One describing a very simple method of measurement and the other a more complex method. The earliest version is that Thales observed the length of the shadow of the pyramid at that hour of the day when a man's shadow is the same length as himself. Plutarch improved on this when he wrote in the Convivium, although he, the king of Egypt, admired you, Thales, for other things, yet he particularly liked the manner by which you measured the height of the pyramid without any trouble or instrument. For by merely placing your staff at the extremity of the shadow which the pyramid cast, you formed, by the impact of the sun's rays, two triangles, and so showed that the height of the pyramid was to the length of the staff in the same ratio as their respective shadows. Both versions of the story depend on the same geometric propositions, namely that the sides of equiangular triangles are proportional. Thales, having thus conceived of two similar triangles, argued that the height h of the pyramid was to the length h of the staff as the length s of the pyramid's shadow was to lengths of the shadows cast by the staff when it was held vertically. Thales knew already the distance along each side of the base of the Great Pyramid was 756 feet and that his staff was 6 feet long. It was necessary only to measure the shadow of the pyramid, the distance from the tip of the shadow to the center of the base of the pyramid, and the shadow of the staff. It was 342 feet from the tip of the pyramid's shadow to the edge of the base, and the shadow of the staff measured 9 feet, as showed in this illustration. Now, Thales had all the required dimensions for 3 items of the proportion would give him the missing 4th item. The height of the Great Pyramid was Using the formula, you just need to substitute, and then the result is 480 feet. According to Proclus, Thales used the congruence theorem, which asserts that a triangle is completely determined if one side and two adjacent angles are known. The most probable assumptions that Thales, observing the ship from the top of a lookout tower, say of height, used the proportionality of the sides of two similar right triangles. All he needed was a simple instrument with two legs forming a right angle so that he could mark off the point E where the line of sight with the ship cut the leg parallel to the ground. This would produce similar triangles A, C, B, and D, C, E. In this illustration, you can say that if x is the unknown distance of the ship, then by properties of similar triangle, one has x over y equals to length plus height over length, or you can use the formula x equals to y times height plus length over length. Another possible approach is that to end the distance x from the shore A to the ship B, one measures from A along a straight line perpendicular to AB an arbitrary length AC and determines its midpoint D. From C, construct a line CE perpendicular AC in a direction opposite to AB, and let E be the point on it which is in a straight line with B and D. Clearly, CE has the same length as AB and CE can be measured so that AB is known. This supposition is open to a different objection. It hardly seems credible that to ascertain the distance of the ship, the observer should have had to reproduce and measure on land an enormous triangle. Such an undertaking would have been so inconvenient as to deprive Thales' discovery of any practical value. In the illustration, it is more likely that triangle ECD was constructed smaller and similar to triangle BAD rather than congruent to it. A legend that reappears from time to time is that he amazed his fellow Greeks by predicting a solar eclipse in 585 BC. Thales' fame as scientist rests mainly on this achievement. It is almost impossible to give credence to the tale. All Thales may well have had some knowledge of cycles of lunar eclipses. They were already known to the Babylonians, but his alleged prediction of the year of a solar eclipse would only have been a fortunate guess. A likely explanation is that he happened to be the wise man known to the people who saw this striking phenomenon, and so they assumed that Thales must have been able to foresee it. Although Thales left no written record of any book or document behind him, he ranks high among mathematicians for his pioneering contribution to the logical development of geometry. He may even have been Pythagoras' teacher. Some sources tell that Thales recognized the genius of the young Pythagoras, to whom he taught all that he knew. That's all, sir. Thank you.